And what I want to talk about today is how we can update CAN bus for all the things we want to do with it in the 21st century. So, CAN bus is amazingly successful, as you might have noticed. Super robust, it's very low cost, that's why it's everywhere, and it's in everything from cars, buses, trucks, spacecraft, and there's even a CAN bus right now orbiting Mars, which is pretty good. But it was created in 1987, and that lots of things today weren't really in the minds of the creators of it. So there wasn't even a global internet in 1987, so the idea that you could hack someone's car from 1987's worldview was inconceivable. And it's too slow now for modern applications, so 500 kilobits per powertrain is about the maximum you can push CAN to, and that's not fast enough. So today we see lots of partitions in a vehicle with multiple CAN buses to try and make up the bandwidth, and that's a lot of wiring, there's gateways between the wiring and stuff, and it's just not a very good solution. But CAN is brilliantly suited to the job, so we should upgrade it. So I'm going to talk to you about how we can augment it for performance and then for security. So, top requirements for augmentation is that it's completely backwardly compatible with it is today, because if we start introducing stuff that doesn't work with existing hardware, then we have to get back to partitioning buses with all the new stuff on one bus and all the old stuff on another bus and moving data around, and it gets to be a right pain. And there's lots of silicon still coming out today that's still running with the classic CAN 2 controllers. So we've got to coexist with all the same CAN controllers on the same bus, and we must use all the same transceivers that are available off the shelf. So it has to be digital side augmentation only. We can't mess around with the physical layer. And it has to work on all the existing wiring. So we can't say, oh, we'll rewire it, put thicker wiring in, or change the wiring system. So it basically has to work with completely the physical layer and legacy devices on the CAN bus. And we want it to go much faster. So we should be aiming at least 10 megabits. And it must have security protections, so we have to protect against spoofing and denial of service attacks on the CAN bus. I'll come to some of that in a minute. So, how do you do that? Well, with some inspiration from the movie industry. So, the movie industry had a problem. So this is a cell here from the 1977 cut of Star Wars. And these little things down here are the audio. That's analog audio, and that was invented in 1920-something. By the movie industry in the US. So, how to upgrade all the audio to modern 7.1 sound, surround sound, and so on. So what they did, this is a Dolby system, is they found there's the analog line, and this is a digital system, and in the gaps between the sprocket holes, they put basically like a gigantic QR code. And you have cameras that look at the sprocket holes, and as the data flies past, the cameras pull out all this digital data, and that's what gets sent in your movie theater. If you take this print to an old-style movie theater, it just plays the analog sound as normal, and everyone's happy. So they've managed to upgrade and augment all the performance of the sound system by putting data in the gaps. So we can do the same with CAN. So here's a CAN bit. 1, 0, 1. And the way CAN works, it has a sample point, and there is a window of where different controllers will sample the signal. And so some will sample a little bit early, some a little bit late, based on clock drift and so on. But if you sample a 0 in CAN, there are rules. So if you sample a 0, CAN completely ignores the state of the CAN line after that sample point until the next one. And that's part of the basic rules of CAN. That's built into all the CAN controllers since 1987. So if we stick extra data after a 0 sample outside of that sample point window and finish with the extra data before the next sample point window, all of that data is ignored by all the existing hardware. But if you've got new hardware, you can pull that data out. So it's just like the movie industry. So normally, say like J1939, that's a 87.5% sample point, and with a little bit of allowance for some clock drift for the crystal accuracy and some time quanta sample jitter in the way CAN sampled bits. You can make a nice little sample point window. So if you allow about 20% of the bit time, the rest of it you can stick in high-speed data. Now, one of the problems is getting high-speed data on CAN bus is the physical layer distorts the signal. So there's asymmetry in the way the transceivers work, so that the rising edge is delayed compared to the falling edge, so the bits get shortened. And then there is the way the CAN controllers deal with reflections from unterminated parts of the end of the bus. So you send out a CAN pulse, and it's like ripples in a pond, and they come bouncing back off the ends of unterminated stubs. And the way that those waveforms interfere can cause timing variations in the pulses as well. And that means there's no simple sample point for a 10 megabit sampling system. So if you're running 10 megabits out in that little gap, there's no one simple place that you can pick that works for across the bus. And that's why CAN FD can't actually generally go above 2 megabits. It's this jittering, if you like, of the signal. But the solution is to understand that jittering around of the signal is not noise. It's not random. It's deterministic through a CAN frame. So it's random when you look at the signal across all the bus from all the different places. But for any given receiver, for any given sender to that receiver, that pattern is a known pattern. It's deterministic because the topology is the same throughout the length of the frame. So if you use calibration system at the start of the frame, you can actually work out how that specific distortion works for the given receiver, and then you can compensate for that distortion, and then you can start sampling data at very high speeds. So we add these very fast bits, and we call them fast bits. Inside classic CAN's dominant bits, so you actually have bits within bits. This really confused the patent examiner when we said there's a bit, several bits inside a bit, and they were like, you can only have a 1 or a 0 state. They got extremely confused, which costs a lot of money when you have to go through the patent attorneys to correct that. So our standardized bits are 104 nanoseconds long. That's 10 megabits a second. They're non-return to zero coding. And every augmented CAN frame has a CAN header of 32 bits. So every single frame that's sent out, you can add 32 bits, no matter what size of frame it is, even including remote frames with no payload. But if you sent out an empty or a carrier frame, we call them, of 8 bytes with a payload of all zeros, you can actually have a CAN body of quite a lot of data. So the headers are used for security. They contain the physical address of where the frame came from. And then the bodies are used to carry lots and lots of data. So if you want to send an 8-byte frame with empty payload, if you like, empty CAN payload, you can squeeze, at 250 kilobits a second, you can squeeze 276 bytes of payload into an 8-byte CAN frame. So here's an example of a logic analyzer trace with our decoder on it. So up here, this is a standard CAN frame, and it's all zeros, and so these are the stuff bits that get put in by the protocol. So that's an empty CAN frame. And then the bottom one is all these little, what looks like random noise. That's all the high-speed CAN data. And these gaps are where the sample points are. You can't quite see them. So here is the 32-bit header. And then for a body, there's a timestamp, a control field, loads and loads and loads of payload, and another CRC. So with inside one of these CAN frames, you've got another frame, a CAN HG frame, which is protected with its own CRC, and it has a header which has its own CRC. So, CAN security. So that's all the high-speed stuff, and you can use that high speed for all kinds of stuff. You can put your signal data in there, or you could use it for sensors. So you can now have a lot of high-bandwidth sensor stuff over CAN instead of 8 bytes. Now, this CAN security, there are two types of attack on CAN bus. Frame attacks, which I call old-school hacks. So you see all these like DEF CON conferences and stuff. They're all doing frame attacks. So you send some spoof frames on the bus, say that you're the engine management system, and make the system crash. That's kind of boring, but still very effective. And then there's the send spoofs with random data to see what happens, which they call fuzzing. That's also fairly boring. And then you can send a huge number of frames on the bus and flood it with loads of traffic, and then it brings it to a crawl, and then the system breaks. So that's flooding. And then protocol attacks, which is the other one, which is the much more interesting one, are attacks on the CAN protocol itself. So if you want to target an ECU, you wait for its CAN frames to come out, and then you blam it with an error frame, and that increments its transmit error count, and you keep doing that 32 times, bang, and it's knocked off the bus, goes bus off, and now that ECU is effectively dead and not communicating on CAN. And that's when you might want to step in then and start spoofing its frames once you've killed it. So here's an example attack here, and this is really cool. This is a little square wave of a particular mark space ratio, and what that does is it causes an error, and then the first one causes an error. The second one is induced in just the right place in the CAN frame to drop into a particular field that triggers what's called an overload frame, which is an old obsolete part of the CAN protocol. So when that was designed in 1987, silicon wasn't fast enough to keep up with CAN. So they have a kind of an X-on flow control thing in CAN. Nothing today generates these frames, but everything has to accept it because it's part of the protocol. So if you break into a CAN's software, you send it a diagnostic command, causes it to crash, set up the PWM, and then send a square wave to the CAN transmit pin of that frequency, that will freeze the bus. And no traffic will go on the bus at all. But crucially, because no one ever sends these frames anymore, most CAN controller hardware doesn't report that as an error, because it's not an error. It doesn't increment the error counts. It's not an error. It's an overload. It just means freeze. And if you just keep doing that in a row, the bus just stops. And there are no errors. No one goes bus off. The CAN controllers most of them don't report that there's an overload frame. It's just frozen. And no one knows why. It's like a freeze frame. And that's a trivial attack to mount. So how do we fix that? So we build with CanHG, because you know where everything's coming from now, you can have a central intrusion detection system that can monitor every CAN frame and look for attacks. So all the anti-spoofing stuff, now you know where the frame physically came from, because you've got the CanHG header that was stuck in there. And now you can tell where it pretends to come from. It pretends to come and pretends to be the engine management system, but actually you know it came from the infotainment. So then you kill the frame with an error code. So you stamp on that frame, so no one receives that CAN frame because the intrusion detection system stamps on it. And then, after it stamps on it, it sends a shutdown command on the bus that says, whoever did that, you're off. And if you've got CanHG hardware, it picks up the shutdown message, and then it disconnects the TX line from the transceiver. So now it can't send anything again. Otherwise, it would just keep resending because it's been an error. It would just keep resending. I mean, that square wave, for example, it would just keep resending. So you cut it off from the transceiver. So the IDPS sends its commands over CAN using a special CanHG, short CanHG frame to kill off the attacker. And then later on, if you want, you could send a reconnect command. It's just like a sin bin in rugby or something. It's like, okay, well, maybe it was a mistake this time round, or we'll try again. Maybe the software malware has gone away. Because a lot of malware, it runs out of RAM. It's put into like a stack overflow or a buffer overflow, and it's not in the flash. So if you go through a power cycle, the malware's gone away usually. So one way to deal with this, if you've got a legacy system and you don't want CanHG controllers, but you've got chips with on-chip controllers, is you put in place a bus guardian. And the bus guardian there is basically a minimal CanHG device, and it takes a CAN signal on the TX and RX pins, or on the TX pin, from the on-chip CAN controller, and then it stitches in a CanHG header, because every CAN frame can have a CanHG header. So the bus guardian stitches in, this is where this CAN frame came from. So the existing CAN software ran into an existing CAN controller on your existing chip on your existing ECU, and it then went through a little tiny chip on the outside of the microcontroller and stitched in, this is where it's come from. And then the intrusion detection system knows where it's come from, can detect all the spoofs, kill them, and then tell this thing to disconnect the microcontroller from the CAN line. Inside that Guardian, there's some very simple CAN protocol detect. So, for example, it detects overload frames, which you should never see from the host. So as soon as that happens, it shuts it off CAN immediately, and then the IDPS can either confirm that shutdown or re-enable it. Okay, so this is available as a Verilog IP block. And it's got an address-based interface to the IP block. And so we've got an SPI command handler front end, so you can have as an external chip, or it could be on chip, either way. And that intrusion detection contains the engine here, which decodes all of those extra Canis G bits and uses a frame table. And the frame table here defines the legal traffic on the bus. So it says, these are the frames that are allowed to be on the bus, this is where they're supposed to come from, and these are the physical addresses. And maybe there are legacy devices that don't have Canis G at all, and it's like, well, this frame shouldn't have a Canis G header, it should actually be a plain CAN frame. And then you know that if, say, for example, the infotainment's got a bus guardian on it, and you start seeing engine management frames with the infotainment address on them, whereas it should have no address at all because it should be a legacy CAN frame, then you know that that's a spoof and you kill it. And it handles automatically the blocking as well. And then in the host system, you run software that will manage the overall security policy of the system. So the idea here is to separate out the mechanisms for shutting stuff down, detecting spoofs and so on, and the policy of whether you do actually kill things off the bus and so on. Because you don't want to embed policy into hardware, because then it's fixed. And so you want your software policy running on a host, running on the intrusion detection system software on the host. So, very quickly, current status. If you go outside, you can talk to Siemens. Their Secure CAV project is using their analytics system. Their analytics system is, in fact, that intrusion detection software on the host that they've developed. And it's got our IDPS 100 inside their big FPGA solution. So it's actually part of their project. It's also under evaluation right now by the United States Army, because it turns out that tanks are actually quite like trucks. They have big diesel engines, and they run J1939 and all the other stuff. Because when you're the Army and you're only buying a few thousand tanks, you don't get to tell people what to make. You have to buy off-the-shelf engines and off-the-shelf engine management systems. And they're very worried about what can happen to ground vehicles if someone was able to inject a square wave onto a CAN bus, for example. And we're right now working on a way of trading robustness and speed. So we're building a new encoding for the fast bits with some new signal processing. And the idea is to, for when the wiring is really poor quality and you've got lots and lots of unterminated stubs and it's a bad piece of CAN physical layer going at a lower speed. And then if your CAN wiring is really good and you've got a really good wiring harness, you can bump the speed up and configure it for different target projects. So I think, based on our early results, we can get to 20 megabits if your wiring harness is good, and it'll be 10 megabits if your wiring harness is bad. So then you can choose, do you want to invest in a wiring harness, or if it's a legacy system, you can't, so you have to stick to 10 megabits, or you could really start to bump this up. And at 20 megabits, we're starting to see, well, actually, do you really need to get rid of CAN for Ethernet in certain applications? That's quite a nice piece of data there. So, more information. I put it up here instead of typing in URLs. You can take a photograph of that and then just go to the QR code. This is probably the most ubiquitous invention from the automotive industry that's gone out into the outside world. I think it was Denso for Toyota, wasn't it, invented the QR code. And then if you don't take a photo, then the URL at the bottom has got a special page on Canis G. So that's how we can bring CAN up to date for the 21st century and keep all the good things about CAN, but make it run faster and be secure.